Class, could I have your attention, please? Let's suppose I've got this thing spinning. Oh, wait, here, we'll do this. We'll spin it the other way. Let's suppose I've got this spinning. Here's a funny thing. I can feel a tension in this string. It feels to me like there's a force flinging this mass to the outside of the circle. But the funny thing is that if I release it when it's right there, well, which way is it going to go? It's being pulled toward the corners, yes? It seems to be being pulled toward the corners, but which way is it going to actually go? Here we go, right into the trash can. Look at that. Did it go in the trash can? That's so sad. All right. Hopefully it didn't land in anything gross, and it didn't. There we go. Yeah. Now, how many people have ever used a sling, as in David slew Goliath? Yes. A sling is an amazingly powerful weapon. We used to take slings and take round river rocks, and we would turn things like basalt and quartz into just a fine powder by slamming them into like concrete walls. Yeah? This is an amazing, powerful thing. And you know that if you want to send it that way, you don't release it when it's there. You release it when it's here, right? So the weird thing is that when an object is moving in a circle, right, it's got, and let me draw a circle for you. Oh, that's a pretty good circle. That's a good circle. That is a pretty good circle. I don't think I could do that again. Oh! I just did do it again. I don't know about that. That's just crazy. That's two good circles. My God.
I don't think you can.
Now, anybody can draw a big circle. Anybody can draw a big circle. It takes a lot of talent to draw a small circle that's any good. That one's not very good. Let's just see. That's sort of good. It's still not. It's below par. Okay? But that's a good circle. That's a good circle. All right. All right. So here is this thing. Here is the anatomy of circular motion. All circular motion has a radius, right? It's got very loud people in the hall. Shut up! Oh, they're a lot quieter now. Okay, this velocity that's happening right here, this is our velocity. This is called a tangential velocity. Yeah, let's say tangential. Shall we say that? Tangential. Nor shall we transpose the T and the I, correct? Yeah. Yeah, there you go. Good. Don't do that. Right? Okay, so this thing is tangential. Tangent means it touches the circle at one spot. And then I don't know if you remember this little trivial thing, but a radius and a tangent at the same point are perpendicular to each other because of math. Yeah? Aren't they? Okay, so in general, we are actually moving tangent to this circle, and we could be going at a constant velocity, yet we are changing direction, and since we are changing direction, we are actually accelerating. Okay, so here's a little chart here. Okay, with the acceleration we've done so far, because remember that velocity is speed plus direction. Do you remember that? Do you remember that? Yes. So far, all we've done when we changed velocity is that we changed the speed. Okay, so for a linear acceleration, the velocity is this way, right? And then the force is this way, and we speed it up, or the force is this way, and we slow it down, right? That's a linear acceleration. What we're talking about now is something called a centripetal acceleration. Right? Centripetal acceleration, the velocity is this way, and the force is just simply to one side. If we're turning right, the force is that way. If we're turning left, the force is that way. So a pure centripetal acceleration, the force is to the side, and the acceleration is to the side. Okay? And that's what these things show, right? Right, so linear is speed changing, right? So the velocity, say, is to the right. Okay, the force is to the right or the left. To the right would speed it up, to the left would slow it down. To the right would be a positive acceleration, to the left would be a negative one, right? And then centripetal acceleration, okay, they're perpendicular. So if I'm moving, say, to the right, if I'm right, then the force, if I'm turning this way and going clockwise, then the force is down. And if I'm going anti-clockwise, then the force is up. And that's just what they say in Britain. They say anti-clockwise. Anti-clockwise. Yeah? So this is a crazy thing. If I am going here, which way is my acceleration? And this is always the difficult thing to figure out, right? Which way am I accelerating if I'm going around in a circle like that? And people always get this wrong because they mistake g-force for acceleration. So let's look at a linear acceleration. Nobody ever gets this one wrong. If I accelerate that way in my car, which way do I feel my body thrown? Backwards. You always feel thrown opposite the direction of acceleration. So in a circle, which way do you feel thrown? To the outside, so you're accelerating inward. Yeah? Now, this is a weird acceleration. Linear acceleration changed the speed but kept the direction the same. Centripetal acceleration changes the direction but keeps the speed the same. Isn't that weird? They're both accelerations, right? But they're just opposites of each other, right? So here, with linear acceleration, speed changes, direction doesn't, is constant. In other words, you don't turn, right? With centripetal acceleration, the direction changes. And then for a pure centripetal acceleration, we just don't change the speed, right? So speed is constant. So an example of a uniform centripetal acceleration is that you go into the middle of a very big parking lot or the Great Salt Lake or something like that, turn the wheel, lock it down, right, and then just put the cruise control on. And your car goes in a big circle around and around. Constant speed, constant radius, around and around you go. And the acceleration is toward the middle. In fact, centripetal, this word with a P, is somewhat unexpected P, that's an adjective that means toward the center. So your goal today is to use the word centripetal in some other context. I've never seen it used outside of physics, but I think you could use that in in politics, right? You know, prior to elections, often people, in order to get elected, their political views tend centripetally, don't they? Toward the center of politics, right? So extreme liberals act a little bit more conservative, and extreme conservatives act a little more liberal. That's not a very good analogy. How about in English class, just say, oh, I noticed that the desks are arranged centripetally today. Does that mean we're having a discussion? Yeah? Yeah, this word, also try to use the word spangled. When was the last time you used the word spangled? Probably when you sang the national anthem, right? The Star Spangled Banner. Yeah? Try to use, what does spangled mean? What does it mean? Does it mean like covered with? Doesn't it? It must be the Star Spangled Banner, right? Yeah? It's spangled with it, right? Try to use spangled for something else, right? The room was spangled with eager students waiting to learn, I don't know. That's right. Try to work that word into polite conversation and have people say, what the heck? Okay. All right. So here is our formula. This is your friend. This acceleration, if you know r and v, this acceleration is v squared over r. Okay? So if you're going, say, 30 meters per second, that's a little bit faster than the speed limit, but not much. Like 27 is like 55, so this is like 60, 65 or something like that, right? Okay? This is for centripetal acceleration. Right? This is our radius of curvature. This is our speed, right? So if you're going 30 meters per second squared over around a corner that is 100 meters in radius, that's a big corner, isn't it? Isn't that a big corner? Yeah, but it's not all that big in terms of like freeway corners are bigger than this. You'll see. Okay, 30 squared is, what is that? Is that 900? Yes, it is. Yeah, so that's 900 divided by 100. That's 9 meters per second squared. Now, here's a funny thing. 9 meters per second squared is a lot of lateral g's. That's nearly a g.